give it a second. Alright guys, sorry. So you should have that in front of you, right? Constant velocity literally means the velocity doesn't change. So we're looking at a constant velocity function, we have a flat line. Now, tell me, if 5 seconds elapsed, and your velocity was 50 meters per second, how far have you traveled?
How many seconds about?
What is it?
250.
200. So if your velocity, did I say 10 or 5?
5.
Okay.
50.
Let's just write it down. If your velocity is a constant and 5 seconds have elapsed, how much position have you covered? 250 meters. Now, how did you get that? I know this sounds ridiculous because it's trivial. You guys have done this, but appease me for now. How did you get that answer? What did you do?
You multiply the velocity by the time.
You multiply velocity by the time. Everybody agrees with that, right? You all agree with that. So do me a favor. On your graph now, label 5 seconds, please. And let's label this height of velocity as 50 meters per second. So if I'm going 50 meters per second for 5 seconds, this is how far I've gone, right? How can I represent that geometrically? Using this graph, how can I show that geometrically? And I'm starting with a simple example for now, and we'll get to more complicated in a moment. What do you think? How can I represent it?
Well, yeah. Well, I remember for integrals, don't you think that the area of the curve?
Yeah, very good. So Kara's already on the right track with the area of the curve for integrals.
Yeah.
So Kara, you want to specifically talk about this one? Up until 5 seconds.
So since it's a straight line, then the integral is a square, a rectangle.
Very good.
And the area of a rectangle is length times, yeah. So you just do that and find the area of a rectangle, and then that value is x.
I think we had like 1 or 2 homework problems that like had this
On your calc or in this class?
in this class.
Did I really?
I think so.
I don't know.
It was like a triangle.
Yeah.
Interesting. And it asked you for the...
It was like a triangle. And I think
So those problems could have also been derivative problems, if you remember. They could be the slope of the line also. It wouldn't necessarily be... Hey, if you did, that's okay. We're gonna get
This
to
was
it.
in pre-calc with like the summer course pre-calc too.
And you took it yourself?
Yeah.
Good. So if you've seen this idea in calc or in pre-calc or at some point along the way, that's a really good starting point. Now, if you haven't, don't worry about it. Don't worry at all. Chris, you focusing? Okay. I don't know what... Okay. Just make sure you're looking up here also. Yes, I don't know. Make sure. So we've got a base length of 5 for the rectangle. We've got a height of 50. Everybody sees that? The base is 5, the height is 50. And it turned out that 5 times 250 gave, 5 times 50 gave us 250. So it turns out that the area underneath this velocity curve gives us our, what word can I use for this?
Position.
Position change, let's use. Position change. Because where did I start? Do I know where I started on that? I have no idea. All I know is that I have a given velocity to start. But I could start at the origin and then move 250. Or I could start 10 meters past the origin and move up to 260. But my change is what's happening. So really, what I'm getting here is my displacement, my change in position. So what I'm recognizing is that the area under a V versus T curve gives change in position. So we're doing this all geometrically today,
Why do you
all
call it a
figures.
curve?
Second?
Why do you call it a curve?
Because a general phrase for any function is a curve. Some are lines, but others are curves. But a line is just a curve with no curvature. So by saying curve, you're generalizing. You could say line, but not all functions are going to be linear, right? They're going to be mainly curved. This is an easy one to start, and did it on purpose so you can see the area concept. In a minute, I'm going to get into what if it's curved, what do we do now, right? So that's where I'm going to extend this idea.
Isn't it also kind of the same idea for A versus T, but it's B?
Yeah, very good. And that would be delta V instead of delta X there. Very good. So what we're looking at in 2.6 is the idea that, you know how we went from position to velocity to acceleration? Now, if we go the other direction, we're simply going to say, well, instead of taking the slope of the graph, we take the area underneath. And the area underneath goes from velocity to change in position, instead of from position to your velocity when you take the derivative. So derivative is slope whereas we're going to use this phrase integral soon. Integral is the area under the curve. And that idea of the area of the curve moves us from either acceleration to velocity or from velocity to position change. Okay, position change. So whenever I want to figure out how much a particle is moved, I don't really need an equation to figure it out. If I'm given a velocity graph, I can just calculate the area underneath. Now, until you get to that point in calculus, we're not going to go into crazy extremes. We're going to talk about it with the power rule, because you guys have done power rule already. Did you get into product rule and quotient rule yet? Nice, okay. So you have the ideas down pat. So we're going to see a little bit of the mathematical work in this course before calculus, so you'll have a head start right there. I saw a hand pop up while I was talking, I'm sorry.
I figured it out.
You figured it out? Okay.
I was gonna ask if like this is like a stuff with like the summation or like sigma.
Yeah. So let me draw a curve and then we're going to see the summation appear. Absolutely. So let's draw a new curve now on the next slide. And let's just draw an arbitrary curve like this. Okay? Sinusoidal maybe, something, right? So I just want to have some curvature to it. Your curve does not have to look like mine. As long as it's curved, put some sort of curve to it. Now, let's say that I knew I wanted to figure out, let's say, the position change, not at, but after 5 seconds here. I put my 5-second mark, I put the dotted line, but then here's the problem, right? This is literally the problem that calculus takes on. So you guys already know the first problem in calculus, which is the derivative. The second problem is the integral. This is all calculus is about right here. Can you figure this out? Now, we're going to get into how we can do it algebraically. But how can we approximate the area maybe? What can we do with that area? Think back to geometry class. How do you get an area of something that's not a perfect shape or not a perfect polygon? Chip, what do you think?
You could like draw a bunch of squares underneath, like rectangles underneath the curve, but like make them really skinny so they take up as much space as possible. Like you increase the surface area by increasing
The missing
width.
piece?
Yeah.
So what is he saying really? What is he using? Give me a more general statement. You're right, totally. A more general statement than that.
Break it up into shapes.
Break it up into shapes. Absolutely. What you said is what we're good at, but I didn't jump to that conclusion yet. We're breaking it up into shapes. So theoretically, I could do this to start. Right? Now watch what I'm going to do. I could say the area under the curve is area 1 plus area 2. Ready for this? Plus area 3 minus area 4.
Where this be? Where is that? 5 seconds. Yeah.
Say again?
You say for after 5 seconds. That's for.
After 5 seconds have elapsed. Sorry.
Oh.
Sorry. Thank you. So what you're noticing is that if I want the area, I can figure out A1 and A3 very easily. A1 and A3 are just rectangles. But then A2 and A4, those are like semicircles or sectors of a circle, regions of a circle. So it's not ideal to use circles, right? And that's what we noticed. But in calculus, the idea in the beginning was, let's put any shape on there. So some calculus people would do this, right? Here's what they would do. They would say, let's approximate this with a triangle, right? Take a look. So let's make area 2 now that triangle, and let's get rid of, take a look, watch what I'm going to do. Let's get rid of this piece now, and instead, let's make this one also kind of like a triangle. It's missing a piece. So now we could do this, and we could say area 1 is a rectangle, that's easy, plus area 2, which is a triangle, plus area 2, which is a triangle. Then area 3, well, I'm going to do this. Take a look at what I'm going to do to area 3. I'm going to break it up further. So I can say area 3 is this rectangle plus these two little triangles here, right? Now, based on looking at this problem, would this be an under or overestimation of the area?
Under.
Why under? Yeah, you're missing these little pieces, right? So let's shade what's missing so we can see that. So we're literally missing what's in green. That's the area that we're not considering by adding up the 4 or 5 shapes, I guess. Yeah, we have 5 shapes now. Okay, there's the 5 shapes. By adding up those 5 shapes, A1, A2, A3, A4, A5, we get an approximate area, but it's not the right area. It's an underestimation. Now, if my shape went beyond the curve, we could say it's an overestimation. But then sometimes the shape might be above the curve, other shapes might be below the curve. So you can have overestimations in one area and under in the other. Maybe they balance each other out. But as Chip mentioned, the easiest way to start a problem like this is either what's called a rectangular approximation or a, Max, you've done Simpson's rule yet? Trapezoidal? Trapezoidal? Simpson's rule, sorry, but trapezoidal, yeah. You could also use trapezoids. So imagine, now let's look at 5 to 10 seconds, please. Let's look over here from 5 to 10. And if I wanted to worry about from 5 to 10 here, instead of using rectangles and triangles, I could then just simply use all rectangles and make them really skinny, as Chip said. Okay, and I could put a lot of those rectangles together and add up all those areas. And that is called a summation, right? Sigma, summation of all those areas. Now, I could also use trapezoids. Trapezoids are really nice, by the way. Take a look how nice this trapezoid will fit. Watch this, ready? I go all the way to the top, and then connect the line all the way to here, and drop it all the way down. And look at that trapezoid I just drew. That doesn't miss much area at all. Okay? It doesn't miss much area at all. And the trapezoid does just as good a job as a rectangle. The thing is, the rectangle you can make infinitely smaller. And calculus is all about the limit as delta x approaches 0. As these rectangles get shorter and shorter and shorter, these little gaps that are missing get fewer and fewer or smaller and smaller and smaller themselves. So the underestimation becomes a better estimation as the rectangles get narrower and narrower. Like if I tried really big rectangles, it wouldn't work. So if I tried a rectangle here, take a look. Look at that big rectangle in blue. Look how much is missing. All this area is missing up here. So it doesn't make sense to make big rectangles, because if I make big rectangles, I'm going to be missing a lot of space. But little rectangles only miss little space. So the goal is, again, to make your rectangles as thin or narrow as possible. So in calculus this year, you're going to learn this technique, and you're going to get into the concept of finding those areas. Okay? But I want you to visualize what an area under the curve is. So back to the beginning, the point we were getting at, though, was that the position change, remember, delta x is going to equal the area under the v versus t curve. Okay, that was the gist of what we're getting at in this idea. Rory, you have a question, sorry.
So even though like the trapezoid like visually may look better in that situation, it's like by far
The rectangle is really slim is the way you want to go down the road. And you're going to see that in math. In this class in here, we're going to really get the idea of it. And most of your functions will be, for now, linear. Like going up, going down. So you can fit triangles and rectangles perfectly instead of curved. I'm going to hold off on the curve for a little bit. I can do one or two of them today so you can see it. But there are a lot of rules you're going to learn in calc that would take 2-3 weeks for you to go through. But I don't want to spend time doing all that because you're going to do it in calc anyway. So I want you to start with the idea of the areas first underneath the curve so you visually understand it. So again, that's the first kind of curve. Let's go to the next one that Kara mentioned. Talk about the idea, well, what if instead it's acceleration versus time? It's acceleration versus time. Again, go back to your proof of it. If I want to know how much velocity I've gained, I can start with this formula right here. The most basic formula I've got. And if I want to see what delta V is, solve for delta V in that formula. You just get A times T. And in this problem, if I had a constant acceleration for a given time period, what will happen is, if I want the area under that curve, and make this dotted, if I want the area under that curve up until 4 seconds, the answer is just what? What's the answer? Good, but what's the actual number I'm saying? 80. So what does that mean, 80? Well, it means that my velocity went up or increased by 80 meters per second. So just like the area under the velocity curve showed me how much my position changed, the area under the acceleration curve will show me how much my velocity changes. And that comes right from this equation. Delta V means change. Change in velocity is just the acceleration times time. The height times the width, or the area under this curve. So that's
So like the area under the curve is the magnitude of how much you change, and the slope is the rate at which you change.
sure. And maybe hold off on the word magnitude, because we're going to start to look into negative areas soon too. So for now, we'll just say it's how much it changed by. It went up by 80. Because if we have area below the curve, it's going to be a negative value, so it's going to go down by 80. So be careful with our magnitude for now.
Wait, so let's say like you had like the acceleration equals 10 meters per second squared. Could you find the difference between those two? But then also do the area.
Oh, sure. So and that's another calc question you're going to get to. That's going to be like in the third quarter of the school year. You're not going to get there. It's called area between curves. So if you had a second acceleration here that was 10 meters per second squared, and you want to know by how much do these these velocities changes differ? Well, at this rate, your velocity change would be 80. At this rate, your velocity change would be 40. So when you double your acceleration, you're doubling your velocity change because these are directly related. Absolutely, you can do that, yeah? And you can even see what this area is right here, and that actually plays a role in calculus later on, okay? But not to jump ahead, I don't want to get into too much of that right now. So here's what I want to do. I wanted to give you guys those ideas. But then what I wanted to see you do is just experiment with a cart track with motion detector so you can visualize and see this yourself. So what I want to do is two things. I want you to have a flat cart or a flat track with a cart moving and a motion detector at the end. Okay, this is just an activity. It's not going to be like a full lab like the full lab. This is just to get you to visualize it. That's all it's for. And then what I want you to do is I want you to incline that cart. We did honors physics. I want you to incline that cart a little bit, send it up the ramp, and then let it return back to the motion detector and stop it right before it hits the detector. Okay, so the first time I want it to be a flat cart, and just give it a push, let it go for a while, and at some point in time, stop the motion detector from collecting the data, look at the position change, because it measures position, then look at the velocity graph, try to figure out the area of the curve, see if they match up, if they don't, and why. Now, they'll be pretty spot on, but there might be discrepancies based on the detector. The second time through, though, when your velocity is going up the ramp, the detector is going to measure that as a positive velocity. But then it's going to start coming down the ramp. So I want you to start to think about that a little bit for the second scenario. Okay? Work for now with the person next to you. That's fine. How much time do we have?
We have 8 minutes.
8 minutes?
Yeah.
Shit. We want to do the first one together, maybe? Let's do the first one together, and then I'll have you guys do the second one by yourself tomorrow. Spence, can you grab me the other track, please?
How big?
Either one is fine for now. Just throw it between these two desks right here. That'd be perfect. Alright. So this is what you're going to pretty much do tomorrow. You're going to set this motion detector up again. Okay, so we'll do the flat version together today so you can see it. Okay, so here's how you're going to start. You're going to zero out the device. Let me connect wireless. Does that LabQuest have a Wi-Fi signal on it on the bottom right?
It does not.
It's showing no Wi-Fi?
Yeah.
Okay, hang on. Because I can show on my computer what that is if it actually has Wi-Fi. I'm just going to grab you a different one for a second. It does take a minute to connect to that, so it might not even work for a little while. Maybe hold off until we're done so see what we can use. It should auto connect if that's not the science that Okay, don't worry about it for now. Just connect the device and I'll see. You might be able to manually do it. Is there an IP IP address on there when you go to system? You go to the Wi-Fi, yeah. Yeah, but the problem is connecting to it. The network is actually connected to it. No, because it has to be the same network my computer's on, then they see each other.
Yeah.
That's the Wi-Fi at school. All right, I'll take a look at that. What we'll do for now, so you can see it, we'll hold it up after. So what we're going to do is we're going to calibrate the sensor. So we're going to choose sensor 0 out, and it's right up against here. M's going to tap the duration. Maybe set it to like 10 seconds, so 5 seconds doesn't run out. Now, what we're going to notice, and I'm personally not going to push this very hard because it's going to go off, and I want it to kind of stop toward the end. And you might have to try this a couple times. So yeah, you start clapping. Yeah. That's way too fast. That's all right. Let's see what happens.
It works the same way.
Position is constant. All right. So for today, guys, normally I would replicate this, but I think it's probably my fault these aren't working. I just did a system update like 2 days ago for all of them, so they didn't need a Wi-Fi. So let's take a look. I know it's tough to see, but the first one here is your position graph. Your position was increasing until it reached the end, and what happened? It stopped, so it stayed constant at the whole end. The velocity, if you look at this, was relatively constant, but it was slowly decreasing. Look at the velocity graph slowly decreasing there. What we can do with these devices is you can actually use statistics on here to actually analyze it a bit better. So I'm going to look only at the velocity graph so you guys can see it a bit better. There's my velocity graph. What I can do is I can find the area under this velocity curve right here. And I can let the graph do all the work for me. So if I go to analyze here, and I think it's under integral, and I can take the integral of velocity, and I can go ahead and I can use this region right here. And what it does is it shades in that region on the LabQuest device. And what does this region tell me? This region, as a sum, comes out to be 0.96. Well, take a look. This is a little over a meter. So if I look at this and I see 0.96 as the integral, and it may not be perfect because I think I missed the beginning part a little bit, but then I go back to my position graph, I can see that it's pretty much at 1 meter when it stopped moving. So the integral of the velocity graph gave me 0.96, and it's practically at 1 meter at this point. So again, proving that the integration of the velocity curve gives you your change in your position. Now, tomorrow what I want you guys, or Thursday what I want you to do when you come in to start, is do the same thing, but have it tilted up so that the velocity is not only positive, but it eventually stops and comes back, and you have negative velocity below the graph. And then I want you to start thinking about what that's going to cause. And you might be able to think about it already. I know some of you are probably already thinking about what the answer is going to be, and that's fine. But I want you to just experiment through that process, okay? I did the homework up already for 2-6. We definitely start that tonight. It's out of Walker, the text. I'm going to put up the multiple choice questions for section 2-6. I haven't done that yet. You guys have the multiple choice chapter 2 document already. It's going to be the ending questions in the multiple choice there, but I have to put the assignment. But the 2-6 homework out of the textbook is already there. I'm going to try to, when I make homework assignments, also put the problem set up at the same time. So today, during 5th period, I'm not only going to put up the solution to the last test for the math problems, but I'm going to add to the problem set assignment for section 2-6. So when you finish the homework for 2-6, maybe tomorrow, the next day, whenever you do it, and then you want to start the problem set maybe over the weekend, you can do that to get a head start. Is that clear for today? Okay? Really good lesson today. I hope you understand what we're doing here. Now, we have not taken the algebraic approach yet at all. So next class, I'll give you guys time to experiment with this on a ramp with different velocities. Then I'll start talking about the algebraic way to do it, and you'll have like a leg up on everybody in calculus. Because it really is useful to at least be able to do it algebraically using the power rule at the minimum. Because that's what most of the functions are. They're either power functions, or you'll start exponential parabolic functions, or trigonometric functions, sine and cosine. Okay, so we'll see how those play a role as well. But tomorrow when you come in, or sorry, Thursday when you guys come in, grab one of these, grab all these materials, and get started right away. Okay?
Clear the data, right?
Yeah, you can clear. You guys can go. Go up and over, guys. Obviously, obviously when you leave quietly, though, whenever you guys go early, because other classes are still in session. Yeah.
Can I come in at